Well, thanks to everybody who has joined us so far. I know people tend to trickle in, but in the interest of time and because we do, try and keep these short, I'm really pleased to be able to welcome Connie Walker to this latest GNOSIS Connect. Connie is a scientist at the U.S. National Center for Optical Infrared Astronomy, which is the National Science Foundation's NOIRLab, has been long involved with light pollution issues. Um, Also, quite a big STEM outreach star, I believe. Interesting young people in the night sky, and has been appointed co-director of the new International Astronomical Union Center. This is a mouthful on the protection of the dark and quiet sky from satellite constellation interference. And as you know, in Gnosis, we're all about getting industry and the science community to work together to understand the challenges and of how to share the space environment and how to let the space environment grow safely and sustainably. And so it's great for us to have Connie sharing her work with us today. So thank you very much. And without further ado, I hand the mic to Connie. Please do introduce yourselves in the chat and also any questions that you have. We'll try and make sure there's a couple minutes for Connie to take those by the end of this, but also just put them in there. If we run out of time, we'll find another way of answering them. So, Connie, welcome. Thank you for joining us.
Well, thank you for that very kind introduction, and thank you to the organizers for inviting me to present. I want to say that this is a team effort. It's not all my work. You had said all my work. No, there's a big, huge team here, and one of the team members is in the audience. That's Mike Peel, and he could answer questions on one of the hubs because he's one of the co-leads. It's called SatHub, and I'll talk more about that later. So today, I'll be talking with you about some of the challenges, solutions, opportunities, with the increasingly large numbers and brightness of satellite constellations, how they impact astronomy, and how we, as part of an international community with the satellite industry and also other astronomers and other stakeholders, can actually work together to protect the night sky for astronomy and for all humanity to enjoy, and without, negatively affecting basically the goals of the satellite companies. And with me on this journey are several leaders of our groups, which we call hubs in the IAU, and we mercifully shorten it to CPS. So you hear me say CPS many times. So satellite connectivity has been effective in providing internet to isolated communities and in monitoring potentially catastrophic situations like the ones listed here. And that said, the proliferation of LEO satellites, particularly in large constellations, are impacting the field of astronomy. So I bring some rays of hope. Mitigation strategies are being developed and undertaken by astronomers and the satellite industry and space policy people and others. And many times these communities are actually working together to provide some solutions. So there's two main challenges to characterize the impact of satellite constellations on optical astronomy. So today I'm only talking about optical astronomy. Sorry, Mike. The first challenge is the exponential growth in the number of satellites in recent years, and especially for commercial satellites in LEO. This number has increased more than fivefold in as many years. So about 10,000 of those satellites are active satellites in the low Earth orbit LEO, and the International Telecommunications Union, which is part of the UN, has a regulatory filings for 1.7 million LEO satellites. And however, realistically, we're probably going to only see 1,000 to 2,000 of these satellites in fruition, get launched in the next few years. And that is still a large number that will be impacting our dark and quiet skies. So the second challenge deals with the brightness of satellites, which can cause bright streaks in optical observations. And the circle at the lower left represents satellites that appear overhead on a midwinter night at a major observatory located in Chile. The yellow dots are illuminated satellites, mostly at twilight, and the grayish black dots are satellites in the Earth's shadow. And the simulation runs from about 3 p.m. in the afternoon to 8 in the morning, and it loops. And the maximum number of bright satellites are about 5% of the ones that are actually there during twilight that you see lit. reflecting. Excuse me. The numbers are very similar to present numbers of active and inactive LEO satellites, but in actuality, this simulation was done 4 years ago, studying what was then the future 12,000 Starlink satellites, Gen 1. And now the future is here. So considering the two main challenges of number and brightness of satellites, what is some of the science that's impacted by the streaks across an image? And most of the observations are done at twilight, and they're done to search for near-Earth objects, and also solar system objects that are basically between the orbits of Earth and Venus. And these observations must be taken in the direction of the rising and setting sun. Observations of these potentially hazardous asteroids then need a very short discovery window to get the many detections required to determine their orbits. If data that could help determine an orbit is lost due to satellite trails, then we lose the probability determination for collision with Earth. And there are 3 other examples listed here. So when our observatory is impacted, so there's I've sort of segregated this into 3 scenarios. One, when there's very narrow fields of view, and there's streaks that are, well, I should say, the streaks that are produced in an image are irretrievably cause a loss of all data that was once where the streaks are now. That's basically when you have a very large field of view. For a narrow field of view, then it's a very small part of the sky that you're actually seeing, so the effect is limited and is predominantly just at twilight. We're going to see maybe up to 10% of the frames that could be affected. And in general, this is something you can deal with through mainly scheduling or just retaking the observations. But for wide field telescopes, there's large portions, obviously, of the night sky that you're seeing, like with the Vera Rubin Observatory, that's going to be, it's now in its final stage of construction. It's going to be operational mid-year or so, and the situation is much more challenging there. And here, that example there, all the frames are going to basically be affected at twilight, and many of the frames during the other parts of the night. So the Vera Rubin Observatory and other wide field facilities they're deploying a lot of substantial resources to figure out mitigation strategies. So we have the instance here where you have, in particular, I give an example for Rubin. They did testing on a section of their very large camera, and they have 3 different scenarios here. One where the satellites that are effectively darkened to about what they call 7th magnitude, and that's just beyond what the human eye can see. And it's a straightforward way to identify and ignore the pixel and the main streak, and it is very straightforward to do this, to just ignore them or mask them, and use the rest of the image if you can for science. But for reference, some of the Starlinks actually achieve some of the 7th magnitude some of the time, not all the time. The middle one, unfortunately, that's despite darkening methods, the current direct-to-cell Starlinks are significantly larger in size and therefore about 5 times brighter than processors. I just lost my, pardon me. And satellites in this magnitude range, it's like 4 to 5 typically for some of the Starlinks. We create sort of secondary stripes or streaks that are caused by something called crosstalk. And this could happen, especially with cameras like with the Rubin. And the main streak is brighter in some areas, more brighter than others. So it's not a linear streak across the image. It changes in size. And so this makes it very, very difficult, those 2 combinations, to actually try to correct. But the worst situation is when you have like hugely bright, like maybe array platform, then hugely reflective, say the brightness of Vega, which is a magnitude of 0, then you get basically saturation or whiteouts, and it looks like the panel on the right-hand side. And here you just have to throw away the data basically, and there's a lot of effort to actually correct for that with maybe more observing time, for instance. Okay, and so you might ask where this 7th magnitude threshold comes from, and I just want to plot this here very, very briefly. You can see that there is on the x-axis there is the satellite apparent magnitude, and it gets fainter to the right. And the pixel count is on the y-axis, and those are bands of frequencies that are going across at optical wavelengths, going diagonally across the plot. And there's a saturation limit that you can see at 100,000 electrons, and then down below you see that there's a range of where you can actually correct the crosstalk below that point. So that's where, if you look at the magnitudes for which they can be corrected, it's between 6th and 7th magnitude mostly. And that's where the threshold, at least for the Rubin, comes from. And that's the worst case scenario. So that's what we use basically as a sort of a litmus test to ask satellite companies to actually try to achieve. But that is at 550 kilometers, and you have obviously satellites at various other distances. And here's a plot that shows you that black line that's going diagonally across, basically shows you that as you go to higher altitudes, you actually have to make the satellite fainter for us not to have that crosstalk effect, which is kind of counterintuitive, but the research has been done on that, and that's the result. And so there's 2 slides now on mitigations, one from the astronomy community and one from the satellite community. And so the potential kind of mitigation strategies, one strategy that the astronomy community has been undertaking include making simulations or models of what, like predicting where and when satellites would appear above an observatory. And this allows, obviously, observations to be scheduled so that satellites could be basically avoided. And that's one thing CPS is working on. And another measure includes simply closing the telescope shutter at an exact moment a satellite passes. And this is not always something an observatory can do. But these strategies either require a knowledge of the precise location of the satellite or having a satellite detection camera. And of course, many observatories don't have that just yet. But for the mitigations for satellite operators, some of the astronomers are actually working on a few strategies with companies. And I'd like to acknowledge the efforts of SpaceX in developing and creating some of those mitigation solutions for their Starlink satellites. Some basic mitigations are listed here. The ones that operators have either done or could do to reduce impacts to optical astronomy. You could launch at lower altitudes, and if that's the case, then there'll be less time during the night that you see the actual satellite crossing your field of view, because they would actually spend more time too in the Earth's shadow if they're at lower altitudes. And SpaceX has lowered some of their satellites, so kudos to them again. Another important mitigation is to use darkening methods to reduce satellite brightness. And SpaceX has actually been implementing some of these things with a coating that reflects light away from the Earth. And this image on the left too gives another one of their mitigation techniques that SpaceX is employing. And they're sharing this too with other companies, how they're doing this. The terminator between night and day on Earth, Starlinks are actually can be adjusted or reoriented in the attitude so that light reflects away from the Earth. Then, of course, the biggest thing, though, is really sharing information. So information like attitude adjustments and planned maneuvers. It's key to avoid things called glints, which are just like one of the brightest events that can happen and to an image in astronomy, optical astronomy. And so that we really need to, this really happens too on orbit rise and orbit descent, as well as when it's tumbling, maybe when it's in orbit. So all phases of a life of a satellite. So sharing too, as I mentioned, the positional data is extremely key to what when we could avoid the satellites and where they would be. So some satellite companies are willing to do this, but there are a lot that are not exactly willing at this point in time. So so to kind of arrive at a solution of how to enable many of these mitigation strategies, we created the center, as you know, that long title that we shortened mercifully to CPS. So CPS is hosted by NOIRLab, which is where I work, and the Square Kilometer Array Observatory for the radio astronomy part of all the efforts were herein. And so the mission of the IAU CPS is basically to research the impact satellite constellations through all the things you might imagine: observations and software, policy, industry and technology, and also community engagement. And we really endeavor to bring together different communities and coordinate efforts and to collect, produce, and freely disseminate information and resources. And these last 2 points are very analogous to the mission of GNOSIS, I think. So we have 4 hubs or groups, and they're led by a robust team of co-leads. You met one, it's Mike appeal. And we have about 450 members from 57 different countries. And we're working actively to try to get them all involved, but we'll see. We've only been in existence 3 years, I have to mention too. So to achieve success in mitigating the impact of satellite constellation interference, we take a multi-pronged approach, and these 4 hubs are integrated collaboratively within the center. And I'm going to talk first about the Community Engagement Hub. Okay, so the Community Engagement Hub has been building awareness by providing forums within which we have guest speakers, and these are aimed towards stakeholders as well as non-astronomy and non-industry communities. And the Community Hub is continually seeking out and establishing contact with new stakeholder groups, and they have a big part in developing the strategic communications plan for CPS and a lot of new informational materials. And one of the best products to date has been their SATCON 101 videos, and that's found on our CPS website. And it's 8 short videos created to inform the public and industry of the challenges and mitigations involved in satellite constellations, basically. So, and the second hub is SatHub, and that's where Mike works. SatHub is a software observations and analysis hub for signatures of commercial LEO satellites in the night sky. So it has this open software source development. And at the moment, that development is focusing on satellite position forecasting and brightness modeling. SatHub also organizes volunteer-led observations and research projects on satellite constellation interference and mitigation. And they do also maintain a data repository for observations. And all these things are being populated now and moving forward at fast paces. But let's just take a slight look in 2 slides on the software development and on the observation network just a little bit further. Sorry, I won't click forward now. Oh, there we go. So one big boost in terms of developing tools for mitigation is we've been funded by the U.S. National Science Foundation on a grant awarded to NOIRLab and the University of Illinois for the benefit of CPS to work on satellite positions and brightness forecasting. Because if you want to know what the brightness of satellites that are above a certain threshold, so those are the ones you really want to target in terms of avoidance. And then we would test these tools on science impacts of with the Rubin Observatory camera and other telescopes. In the past year, SatHub software team has been creating the prediction software tool called SatChecker and a data repository called SCORE. And so to incorporate in the future more precise positions and brightness predictions, we will have access to a database of satellite orbits cleared by the U.S. government through a company called Aerospace that we're working with, and access to also brightness model parameters created by Fankhauser et al. As part of Tony Tyson's group at UC Davis. And in order to avoid satellites, an astronomer at an observatory anywhere in the world is going to be able to use this new product, SatChecker, to predict the position of satellites for a threshold brightness as seen by their observatory within their telescope's field of view. Now, in terms of the observation efforts, we have volunteer-led observation campaigns with contributions from individuals and groups all over the world. And some of the main goals of the observations are to measure brightnesses, study glints and flares, properties, and assess mitigation efficacy, measure science impacts, and publish results. And the observatories, the observations network has done campaigns for Starlink. They have a direct-to-cell at lower altitude, and it's much larger and has a visual magnitude of about 4 or 5 right now that I mentioned before. That's 5 times larger than the previous satellites that they had. So, or brighter, I should say, not and larger, but 5 times brighter. And there's other ongoing campaigns with other companies like Planet Labs with their Pelican and Tanager satellites, and they're around 7th magnitude right now. And Chinese Thousand Sails and Amazon Kuiper, we've started to observe as well. Companies such as Starlink and Planet Labs and Kuiper have asked us actually to make observations on the brightnesses of their satellites, and that's in order to inform them basically how to mitigate the designs maybe for their next generation of satellites. That's the hope, and that's the goal of one of the goals of the network. So one of the CPS most important publications I just want to highlight, because we've had many, but one of the most important ones is about the direct-to-cell satellite from AST Space Mobile called Blue Walker 3, and that was measured to have a brightness of 0th magnitude, as bright as Vega, one of the brightest stars in the night sky. and the results are plotted to on the left-hand side. So the thing is that when it unfurled, before it unfurled, it was like 7th magnitude. After it unfurled, two of the satellites one was 25 times brighter than the 7th magnitude, and the other was 48 times brighter. So it was hugely bright. So the next generation of Blue Orca 3s are going to be bigger and brighter, and we're hoping they're going to employ some of the mitigation techniques. And the last two hubs on policy and industry, and I'll tell you a little bit about them and what they have done to mitigate the brightness of satellites. So the aim of the Policy Hub is to study the national and international policy and regulations related to the use of space, and in particular to satellite constellations. The Policy Hub coordinates and supports the work of national groups on these topics, and also supports actors in the international policy forums, such as the UN Committee for the Peaceful Use of Outer Space, you hear me say COPUS, as well as the International Telecommunications Union. And the Policy Hub has been involved as an advisory, sort of an advisory capacity, with some exceptional opportunities and accomplishments. And they have ensured that Dark and Quiet Skies is included, for instance, in all the things listed here. And I want to highlight two of them, and that's the U.S. National Science Foundation Coordination Agreements as a condition of FCC licensing. And the last one I want to kind of highlight is a new 5-year agenda item on Dark and Quiet Skies and satellites at the UN. And I'll do that in the next 2 slides very briefly. So in June of last year, in 2024, the UN Committee for the Peaceful Use of Outer Space agreed to include the agenda item of Dark and Quiet Skies, astronomy, and large constellations as part of its agenda. And that's a big accomplishment. It took us about 4 or 5 years to get there. And this will be from 2025 to 2029. They already met in February of this year. Many sponsors, including the CPS and its Policy Hub, were behind this achievement in an advisory role. Chile, Spain, the UK, U.S. State Department, and others have been very prominent participants, and they and others have formed this group of friends and are now actively working to report out and develop Dark and Quiet Skies agenda items for the next meeting in February 2026. And this example is of a national example. It's the U.S. Federal Communications Commission. It licenses commercial satellite operators, and in that licensing, the FCC is now imposing conditions such as the 4 listed here, obvious things about the brightness limit, about the limit in hopefully in how high they can go for the reasons I gave before, and how orienting satellites so that they don't reflect sunlight towards Earth, and providing telemetry, orbital telemetry information of where they are so that the telescopes can avoid the satellites. So these conditions are specified in a NSF coordination agreement with SpaceX, and they've agreed to it. And similar conditions are now with agreements with 3 other companies, and hopefully more in the future. So the last hub is the Industry and Technology Hub, and I'll say INT sometimes. And it's been a lifeline to engaging satellite companies as pathways to converging on possible mitigations. And they have successfully recruited 16 satellite companies that really interactively work to provide a safe zone for discussions and sharing of information. And the INT Hub has provided background fundamentals and updates on astronomy concerns to these operators and manufacturers, and they have synthesized existing recommendations that have been made and best practices as well to provide the stakeholders, the operators and manufacturers with more understanding of where all this is coming from. And they have created a directory of available mitigation technologies and tools like reflectivity testing of the surfaces of satellites. And they've also launched, the one I like a lot is the Astronomy Guide program, and this partners astronomers with companies so they can actually ask questions to the astronomer and become more informed and more comfortable. And with that, I want to just give you one of 2 final slides, and here's a couple of take-home messages. And the first is that the large and increasing number of satellite constellations will impact quantity and the quality of science possible from ground-based facilities, as well as potentially change the appearance of the night sky, and it will. A combination of mitigation techniques like the software development we talked about, observations, policy, industry relations, can reduce light brightness for the benefit of astronomy, space science, and all sky observers, as well as for our cultural heritage of humanity. And we are working collaboratively with industry stakeholders and governmental bodies worldwide to reduce this impact. But even though the IAU CPS is working along these lines with promising results, the situation is quickly evolving, involving more countries with satellites and possibly larger and more impactful satellites that'll be even brighter. So to ultimately remain effective, these best practices need to be acknowledged and supported by governments from which these companies depend. And with that, I just want to give you our contact information and feel free to contact our team at any time. And thank you for your attention. I'm very, very happy now to take any questions. Thank you.
Thank you so much, Connie. A lot of information packed in there, and it may seem like it has been slow progress, but actually, given how little time constellation networks have been in existence, that feels to me like although the astronomy community is slightly running to catch up, you've had an enormous impact in just a few short years of working
Thank
on the
you.
issue. There's a question in the chat from David Lowe at the UK Space Agency. David, do you want to come on and put that directly? If not,
Sure.
yeah.
Yeah, absolutely. So yeah, thanks, Connie. That was really, really interesting. I was just yeah, I'm working on like UK policy for dark and quiet skies and mainly on the optical side. But I understand that the question I had was around the FCC requirement for astronomers and operators to coordinate. I know you put that up on the slide. I'm just wondering what, like in practice, what that actually looks like. You know, is it effective and is it enforceable? So yeah.
It is effective with SpaceX. Done, they have put in a lot of effort, a lot of funding to actually, let me try to get back to the, yeah, to actually try to come up with different techniques. They come up with three different techniques, and they had to kind of deactivate the first two for various technical reasons. And now the third one is basically one that they're using both a special paint that's looks blue, but actually reflects quite well away from curved surfaces. And on the flat surfaces, they have this sort of Bragg cell that's like a mirror that reflects light in a different direction away from the Earth. And of course, and I mentioned the other technique too that they use for adjusting attitude. But yeah, and they have sat down with the NSF and actually helped frame this, was with our recommendations actually that came out of a bunch of conferences that started right before that we all had a part in, right before we established the CPS, and it continued to be part of the policy of the CPS. And this framed what went into the first communications. I'm sorry, the first agreement, and with SpaceX. That was the first agreement, and that is now being translated to three other companies. And I've only seen the section, to be honest with you, I've only seen the section of these agreements that pertain to these kind of lines that I have here, not the whole thing, because the companies on the whole, we have found, are very, very private. They do not like to divulge a lot of knowledge unless they really have to. And a lot of it is just to protect their investments, their interest, right? And because they are businesses. And so we have learned a lot about the industry community. We actually started more than 3 years ago to meet with like SpaceX and since then other companies, and to understand that their culture and respect it, because we're not going to get anywhere unless we reach compromises. So for the other companies, they're going to be slightly different because they put in their tweaks and what they can do feasibly. And so I don't know how different they are. At some point, I was told that I'd be probably this will be shared with me in some part, but not at the moment. But it's promising, though. This is all voluntary. It's not. You're right. It cannot be enforced, and it's showing that they're good citizens. And I think, in some respect, they want to be seen as good citizens and do whatever they can in order for the field of astronomy to continue making the wonderful discoveries that it does. Right.
I
Yeah.
think
Okay.
also, sorry, go on, David. I didn't mean to
No, no,
cut.
no. I was just going to say thank you. No, thank you for the answer.
Mm-hmm.
Um,
Well, you're welcome.
I mean, I suppose actually the astronomy community is able to monitor compliance with that because you're gathering the data
Yeah.
on brightness. I'm going to just put a question from the chat. Matt O'Donnell says that he can't put his mic and video on with the browser he's using. So he was asking about the sort of information that's being shared. It's sort of not just the reflectivity, I presume, of the materials, the surface of the satellite, but his question is, the 16 operators that you're working with, are they sharing position and attitude information? And can I put a supplementary on that from me, which is how real time is that information for you? Because now that constellation, in particular, constellation operators are using more autonomous maneuvering, you know, they're not getting that involved. It's not a planned maneuver. It's just those decisions are kind of being made in real time on board, and the
Right.
satellites are maneuvering of their own accord. And so, is that information being shared with astronomers?
Not exactly. A lot of the companies get their TLEs from Space Track and Celestrack, and that's where we're basically getting them now. We have position data that's available from SpaceX, and I think some of the other prominent companies might be giving some of their data to us in the future. We have data from companies like Slingshot, which is basically a think tank, and we are working with aerospace, and because they're part of our proposal with the NSF, to eventually, hopefully in the next year or so, get the something called TRACS, a special program called TRACS, positional data, just the outcome of that black box. We'll get positional data, and that's much more accurate, so that it's less than 8 hours updates, hopefully, and so my ears are not made for AirPods, sorry. Um, and so that's about the best we can do. The companies are not quite as forthcoming as we'd like them to be, but I think with time, there may be some kind of plan that can work out for some of the companies.
Well,
And
if
Mike, oh, sorry, go ahead.
no, do go on.
I was going to ask if Mike had any more insight he wanted to share.
Mike, can you? Oh, no more than what you've
No,
said.
no. Thank you.
So,
Okay.
James had a question.
Thanks, Catherine, and thanks, Connie, for the excellent talk. I
Thank you.
was just wondering about the point that you made that I think you mentioned was slightly counterintuitive, where the recommended brightness actually gets fainter as you go higher in altitude. Is that due to the fact that they have higher capacity to remain in a given field of view for longer because of their slower motion on sky?
Well, that is part of it. Yes, definitely. So that's a very good question, and yes, that's part of it, definitely.
Thank you.
If you have time for just, one more question, I know we're slightly running over. It's great to see the progress that you're making with some constellation operators. My question is that, there are other countries where constellations are being developed. China comes to mind, immediately with its very ambitious plans, but other countries as well. How is the dialogue going with other countries outside of sort of, the Western countries? Do you have hubs all around the world? Is there, a dialogue taking place? Um, those are my questions really about those
Yeah.
other countries.
No,
Yeah.
that's a very insightful question. Um, the answer is yeah. Well, through things like the Group of Friends, which is the delegates from the UN, we have a representation in various nations, and especially the nations that are going to be launching and the ones that have already launched. So very strong relationships with the UK, for instance, and the various things that are being done there. Kudos to you, and kudos to the also the Zero Debris Charter and others that happened. That include dark and quiet skies, actually. So, and also, so that's a way of reaching nations that have the companies and being able to talk with them in some capacity. And also the hubs the hubs are within the hubs, they're international. So it's not like we have a solid hub in every country. It's just that the people are members internationally, and they, especially with the policy group, for instance, which has a big bearing on this topic that you're asking about. And they're trying very hard. But with China, nothing is, let me say, nothing is finalized at all with countries. It's still very much of a dialogue. Each have their own parameters with which they work that are different. I mean, in the US, you have to get licensed, right? In any country, you have to get licensed, but things that fly over from other countries, and do not operate in the US, don't have to have the license from the US. So that they're not restricted in that way, right? So there's those kind of instances, especially China. And China, we're trying to make inroads right now, but we can't really talk with the companies. The companies are actually arms of the government. They're not their own entity. And so that makes it very difficult for them to be able to share anything, and difficult for us to talk with them. So we are trying to make a headway with people that are in, like NAOC, which is their National Astronomy Center. And I think that will go well, but that'll take some more time. And that's a long answer, but
Yes. Yeah.
there you have it.
But it is heartening to see it being added as an agenda item for UN
Yes.
Bodies, because the UN probably is still, you need a dual-pronged approach, don't you? You need collaboration through the science channels, and you also need really collaboration in those multilateral fora where more formal conversations can take place, but all the member states are represented. So that's great progress to see that there. Well, I'm going to wrap that up there. And thanks to the people who were able to join us live. I know lots of people registered and expressed an interest, so I expect to see people catching up with the recording on our YouTube channel. We will definitely send a message out as soon as that's up and available to everybody. I just wanted to say that our next GNOSIS Connect, Teresa, you're going to have to give me the date. It's coming up in April. And we will have Max Alexander join us to talk about his recent work on space weather, and his photography exhibition that explores that and the relationship of space sustainability and space weather. So without any further ado, just thank you very much, Connie. Could everyone please give Connie an actual and a virtual round of applause for your time? Thank you so much.
Thank you very much for having me here. I really appreciate it. Yeah. You guys are great.
Max's webinar is on the 22nd of April, Catherine.
22nd of April. Thank you. Yeah. Well, I hope we'll see all of you then. Have a good rest of your day and a good weekend.
Thank you. Thank you so much.
Thank you. Take care. Bye-bye.